Okay, so I think it's time to start. So hello everyone. So welcome to the system engineer the roundtable seminar this semester. So I will introduce myself first since I'm also new here. So my name is Qianzhi Zhang. I'm a postdoc in system engineer and attending in this June. So it's a great pleasure to introduce our speaker today. So Dr. Feng received his PhD degree from the School of the Industrial and System Engineering at the Georgia Institute of the Technology in 2013. He is the principal computational scientist and a section leader with the Energy System Division at the Argonne National Lab. His current research interests include the power system modeling and optimization, electricity market, power grid resiliency, machine learning, and data analytics. So okay, so with this, I will pass it to Dr. Feng.
Okay, thank you. Thanks for the invitation to this nice seminar series. So my talk today would be a learning-enhanced optimization framework for routinely solved optimization problems. So, I mean, you see the machine learning for optimization a lot, so I added routinely solved here. Does this have the limitedness? We will see later. All right, so I know there are a lot of students here, so I will begin my presentation with the introduction to Argonne because it's a less known research institute. So Argonne is one of the 20-plus national labs owned by the Department of Energy. It's currently operated by the University of Chicago. So that has been established in 1946. One of the earlier projects, I think the Manhattan Project, and later this sustainable nuclear reactor was first built at Argonne. And our annual budget is 1.1 billion. So we have a lot of areas. It's just like a university. We have mathematical computer science, clean energy, this high physics, high energy physics, quantum, and some other things that I never touched. And also we have been recognized in a number of criteria. So currently we have a number of facilities that provide the research tools for people in different fields. Like the first one, the advanced photon source is accelerator. And we have also a linear accelerator that can help people to study the materials, drug development. And we also have the supercomputer, I think maybe top 3 in the US. Also, we have the Nanoscience Center, and so basically it's just like a university without teaching. And we have 1,700 staff, 300 postdocs, and you see that we have nearly 6,000 facility users. So these are the people around the world coming to Argonne to use the supercomputer, to use the accelerator. And you see there are a huge number of students, 500 students. So every summer we have a surge of population because of the summer students. So I would like to mention that Argonne provide internship opportunities not only for graduate but also for undergraduate. There is a Department of Energy program called SULI, S-U-L-I. You can Google it. So basically, you are funded by the Department of Energy, and you can choose one of the national labs to work in. So there are about 20 labs you can choose, and there are a few majors. And also, we have a very flexible internship position for graduates. If you're interested in this very diversified environment and get closer to the real problem, I highly encourage you to consider the internship program at any of the national labs. And also we work with the industry a lot. So the national lab is kind of in between the industry and the academia. So we work on the problems that are closer to the industry. So we expect solutions that are going to be help the industry in the next 5 to 10 years. So that's a short introduction to the organization I'm coming from. So the talk is based on the following 2 papers. The first one is published 2021. It's learning to solve large-scale security constraint unit complement problem. The second one is based on the a recent work exploiting instance and variable similarity to improve the learning-enhanced branching. So Alison Shaver is my colleague, very talented guy. Shabir Zentrudi are professors at Georgia Tech. Xiaoyi Gu is a PhD student at Georgia Tech, just recently graduated. So this is the summary of our results in the 2 papers. All right, so a little bit of introduction to the power grid. And so how many of you know power grid? Okay, so maybe this is for the half. So this is the very simplified power grid. You have the bus, and you have the generator, G1, G2, G3, and this triangle, these are the load. So basically, this represents the customer who demands the electricity, and this represents the generator. You have a thermal generator, you have a wind farm or solar farm, so this represents all that kind of generator. And these lines are the network connect the supply side to the demand side. These are transmission network. So basically, you can consider this as a network flow, but this network flow is governed by certain physical laws. And so the problem here, security constraint unit complement, essentially is to find the optimal generating schedules for these things, turn on, turn off, and how much power it should output to make the supply and the demand imbalance in real time. So that's a very fundamental operational problem in a power grid. And let me give you a little bit of motivation on this. So this is the single most important mixed integer program in the power system. And you consider the electricity market in US annually, which is 400 billion per year. So usually the power market solves the SAUC, security constraint unit complement, in 30 minutes. Whatever solution comes out of that time window, you take it and publish it to the market. And so normally the optimality gap for this MIP is set to 0.1 percentage. So you can imagine that any fractional you improve on the MIP gap, that could indicate hundreds of millions of potential savings, right? So that's a motivation here. Now this problem becomes more and more challenging. You have new energy components, combined cycle, DERs, energy storage. All these things are just recent years, so they have not been in the formulation yet. And also you have other business models such as aggregator, right? And of course, you have a lot of uncertainty with the renewable energy integrated. And also, the market operator want to be more precise. They want to go to 15-minute commitment, but right now it's hourly commitment. So you can imagine that with all these things integrated to your problem, the computational challenge would be very big. Currently, we talked with the MISO, which is one of the largest operator in US. They said that sometimes their MIP gap could be 10%. So you can imagine that that's a lot of money there on stake. So as an optimizer, when you are looking at this mixed integer program, minimizing something subject to and have constraint here, so the first thing you think about is maybe some MIP approach, such as cutting plans, where you can tighten the lower bound, or you can find some strong formulation, which people have found like strong formulation for part of the problem. For example, there are certain constraints, they find a better formulation. Also decomposition, like Lagrangian decomposition has been used in the past. So all these things, unfortunately, does not work when you are going to a real system scale problem, such as if you have like 5,000 bus, 1,000 generators. So all these things does not work. Now we have a problem, very challenging to solve. So how did we come up with this learning enhanced approach? So that goes back to 2016. So when I was working on a production cost modeling project, where you have the whole year production cost modeling, where you solve each day a security constraint unit commitment problem, and for 365 days, every day, you feed the data to the model, and then you solve it, and you come to the second day. So when you do this kind of project, like for like months, you just realize that every day you feed the similar data to the problem. Like the network are same, the set of generators are same. The only thing different is that the demand on the right-hand side, and also sometimes you have different cost curve on the objective. So essentially, you are solving a MIP with the whole left-hand matrix identical, just with a little bit perturbation on the right-hand side. So you kind of like realize that why I'm solving every iteration from scratch. And then you just realize that this actually is the scenario in most every real-world application. Just for example, I mean, in the power industry, no need to say, every day you solve the unit commitment problem in one ISO, same network, same generator. If you look at the transportation system, they also have the same set of road network, same set of vehicles, but only thing different is the demand at each location, right? And they solve this problem every day, repeatedly. So this actually is the real context where the optimization are solved. It's not like you look at a problem, you solve from scratch, and the next day you look at a different problem. So in a real application, you are looking at the same problem every day, every time. So that gives us some this inspiration from the linear programming. Like in a linear programming, you have the sensitivity analysis. You perturb the right-hand side, then you have many ways to reach to the next solutions very quickly, warm starting. So that's kind of inspire us to maybe something we can do for the integer programming. So we have integer programming here, and if you perturb your right-hand side, there are some theories there. like telling you how the optimal solution or the objective will change. So there are some theories already developed, and there are some open source solver that can perform this kind of warm starting on the from the branch and bound tree. So I hired a student from Lehigh University who are working on the coin OS solver and trying to take advantage of this repeatedly solving problem and see if we can make something useful out of it. For example, when you solve the MIP, you have a branch and bound tree, then you have a lot of dual bonds, right? So when you perturb the right-hand side, your dual bonds, you just plug in and multiply. So we have tried different things for 1 year, but at the end of the year, nothing good we got. So the lesson learned that we really need something simple, and also we can't rely on the open source solver. We have to work with the state-of-art commercial solver, so that everything you achieved can transform to the real benefits in the real world. So basically, if you look at the most industry optimization applications, like the unit components, so every day they feed the problem with a set of data, solve it. After they solve it, they took the solution for pricing.
You know how to stop sharing?
So that's a huge waste of information, because every day you solve it, you use a solution, and next day you populate the model again and solving from scratch. So maybe this sounds very regular. That's how you look at the problem. But 6 years ago.
So you can screen share it.
All right. So basically, the idea we come up with is that
This is the one we're projecting.
why we are dropping this information. For example, the feasible solution, right? A lot of you know that if I started solving a MIP with the feasible solution, it could help, right? So since you solved the problem yesterday, which is very similar to the problem today,
So that's good.
why abandon those information? Start from scratch, right? So you can see that there are a lot of things from the past we can use. So what do we propose that after each solve, we don't discard information. We collect it and develop a machine learning model. And those learned strategy can help us to solve the problem in the next. So maybe this is a very simple idea, but I really think this is the, a way to solve a very challenging problem, because, whenever you have a problem very challenging shows up, and you have a mathematician, you have OR guys, you have a, great optimizer, they focus on the, structure, and they work on the cutting plan or develop some decomposition algorithm. So each problem you need a set of mathematicians to work on that. But here we propose that let machine learning do the job. Let artificial intelligence do the job. And for each of we don't want like solution beautifully, elegantly solve every integer program, but we just want an expert that can quickly solve that particular application. So that's the key point here. So, all right. So this is just a a simple diagram. So in the past we do this, we just discard, but now we learn and feed back to the tomorrow solution. So I'm going to start with a problem-specific learning things, but you can see that these are quite general for many mixed integer programs. So one thing we look at is this security constraints. What is security constraints? Security constraints just restrict the power flow on each line. You have many of these constraints in the problem, because for each line, you need to consider the possibility of every other line fail. So you have 100 lines, and you have 100 lines to monitor, And each of them have 99 contingency. So you can imagine you have n squares, this kind of contingency, and they are very dense. So these are your variables, and these things shows up in every single component. So this is a very dense matrix, and that just crash your performance. But in reality, very fractional number of this are actually necessary. For example, we talked to MISO. They told us that every hour they only have like 20 to 30. These lines are binding, are actually necessary. So, but how to predict which one are necessary is not that trivial. So we have we developed the prediction model. So basically, you just look at all the problem you solve in the past and select the most closest one. I mean, there are some definition of closeness, right? And then you look at what lines are contingent, are binding in those programs. And this is a very simple, like, machine learning model. You just pick them. And then that can help you to eliminate a lot of these redundant constraints. But you can see we're talking about redundant constraint here, which is common in any mid-integer program. And the second thing is about the initial feasible solutions. And so in the SAUC problem, we have observed that the solver can do a very good job at the lower bound. But for the upper bound, which is a good quality feasible solution, it takes a lot of time. And so we choose to find a good feasible solution for these instances by looking at the solutions from the past. And of course, again, you can define some closed lists, right? And then you pick the feasible solutions or optimal solutions from the past instance. And you can do like the nearest neighborhood, a very simple model to pick the good quality feasible solutions. And even that feasible solution are not complete. You can look at the partial one. For example, you have a bunch of solutions, but some of them have the same value, so you can just build a partial solution, and the MIP solver can help you to find the rest. So that's a feasible solution. And the next one is the affine subspace. So it has a fancy name, but essentially it's just like some pattern in your optimal solution. So what's your optimal solution going to look like? So if you are a human system operator, give you a system, you don't even need to solve a optimization problem. You know this generator will be on for the base load, that generator will be on during the peak load, right? So you already accumulated this knowledge in the past. So basically, we are trying to replicate this, the human experience, with artificial intelligence. So we are focusing on certain optimal solution patterns. For example, the first one is the generator turned off. Generator is turned on, and the generator's status does not change. And you can have more sophisticated, this pattern or hyperplans. Like you have a group generator, maybe you can learn it. But we focus on this very simple pattern here. And it's a little bit tricky because this is the heuristic. You kind of fix your solution into some like a suboptimal space, right? So you want to be careful. And when you have a machine learning model, if you don't trust the prediction accuracy, you don't fix it. Unless you are, if you are very confident about the prediction accuracy, then you apply this, variable fixing things. So this is this chart shows how much variable we can fix. These are real instance, like real size instances. This size system is almost the same as MISO instances. So one of the largest power markets in the US. And you can see that on average we can do the first fixing 13%, and fix 1, 60%. And for the continuous, for the consecutive time period, the generator status, we can fix near 20%. And in the end, we're only left with a problem with 6% free variables. So this is like a significant reduction on the problem side. And the precision, you can see that is very high.
So when you're doing this, are you just looking at the variable values in the past, or are you also using some right-hand sides, demands in the past as well, and then look at what you have?
Yeah. So basically, you look at the problem instant, for example, like the cost curve, the peak period demand. A lot of the system, characteristic. Yeah, like the right-hand side. Yeah. Thank you. So this is a simple idea here, but it works extremely well. Let me show you some result. So these are our instances, and we try to make the instance as real as possible. So we go to the ISO website and try to download their bidding offer, and we even developed some machine learning model to predict the demand, a lot of things, and this is the variation of the demand. So you can see that we're not making the case very easy, very trivial, right? So there is significant variation on the demand. So that makes your UC solutions quite different every time you solve it. So this is our results, and this blue, this green-ish bars, we don't do any machine learning. And then we do the transmission, we do the warm starting, and then we do the fixing. So this bar is actually heuristic, right? This does not guarantee any optimality. But you can see that for the real system, we can bring down the solution time from 500 seconds to, I think this is like less than 1 minute. So this is a huge reduction on the time. And the solution quality does not degrade for even when you do this variable fixing things. It's still within the 0.1% optimality gap. So you are not sacrificing solution quality for speed. All right, so
can I shortly recap the high level, try to understand what you're talking about? So you have an instance, say demand projection for tomorrow, right? And also you know that green energy kind of labor tomorrow predicts that, right? That's something each day is a variable, right?
yeah.
So you have that input, then you use based on the machine learning model. You have a few options. In the past, you solved many problems, so you have a few feasible suggest the solution, right? And some of these solutions you plug into there is not feasible. So you need to do some tweak, some change to make it feasible. Is that right? Then among these feasible ones, then maybe 10 of them try to find the best one or something, or even start optimization starting from this feasible 10 solutions and improve further. Is that your general idea that you're doing?
Yeah. You're trying to look at a very similar instance from past, and you can give the solution, like you said, and also you can remove a lot of constraints, redundant constraints, and also you can fix variables.
But how do you make it feasible? I guess that's maybe the higher, high order issue. Right?
Yeah. So basically, you don't work on the continuous variable. So this is like a mixed integer program, and there are continuous variables there. So you focus on the binary variables, and so that's because most of the infeasibility comes from the the balance, power balance. And the other thing that if you're not sure you're going to get a feasible solution, you don't touch it. You leave to the solver to solve it. Yeah. Of course, you might get stuck in some suboptimality, but if you do that carefully, our experience shows that you still have very high solution quality. Yeah. Okay. So I just stop here to summarize what I just talked about. So you see, we deal with the security constraints. We deal with this, the solution pattern, optimal solution pattern, and also feasible solution. So these are very common to every mixed integer program. So I'm going to talk about a little bit branch, and then I'm talk about a very general product. So this is the branch and bound framework. For those of you who are not familiar with this, basically all the integer program in the commercial solver are solved by the branch and bound algorithm. And first you relax the problem to an integer programming, and then you solve it, and then you have a bunch of fractional solutions. Then you look at each of the fractional variables, and you select the subproblem where give you the best bound, and you keep diving on those things, and then some nodes integer, some node infeasible, some node suboptimal. You just keep doing this until you prove optimality. All right. Okay. So the branching is one of the critical decisions in the branch and bound algorithm that impact the solution time. And so in branching, there are two decisions you need to make. So one is the node selection. But for node selection, it's kind of trivial because people already know that whenever you select the node with the worst bound, then that's a bad strategy. But for the variable to branch on, this is the tricky. So people have done a lot of research on this. For example, they found out that the most infeasible branching, where you select the most fractional variable to branch on, that is the cheapest one, but the worst one. And then on the other side, you have the strong branching, which is very good. So basically, for every fractional variables, you branch on and you branch up, and you look at what is the objective value change on these two decisions, right? And then you select the one give you the most objective value change. But this is very expensive because for every node, every variable, you will do this. So there are something in between where it's called reliability branching, which is at each node you only probe lambda variables, and during the whole process you only perform eta number of probes. So this is the kind of like a simpler version of the strong branching. And so people have done the things on this many years. So the benchmark we choose is this one, Alvarez. So basically, they look at all the information during the branch and bound, like static information such as your input data, and there are some dynamic problem features such as the information on each branch and bound node, and also some dynamic optimization feature. So the idea is that they train this model for many different type of problems, and then they want to have like a single machine learning model that specializes in doing the branching idea. So this is like if this is successful, then this could replace anything in the branching things. But our idea is that since for each of these like grid operators, they don't care about traveling salesman problem. They don't care about the facility location. they only care about the unit complement. Why do we need a like very general machine learning model, right? So the idea is that let's just focus on one problem. And for each of the variables, I'm going to develop a machine learning model that only predicts that variable. So this is a like similar idea, but focused on one variable, right? And so that's and also there's something in between. Instead of having every variable develop a machine learning model, you can look at a set of variables that are related. For example, for one generator, you have 24 variables, right? Each time period, you have the static variable. So for those 24 variables, I only develop one machine learning model. So this is called grouping. And you can also group by generator, or you group by time, or you just group by the name. So now we have a very specialized machine learning model, and we have to do a lot of work to do the training. For example, like you know, in the commercial solver, when you trying to interfere with this branch and bound, you got a lot of unpredictable behavior. So we developed our homemade branch and bound MIP solver, which only it's a very simple program, just to do branch and bound. And we use Groovy for solving LPs. And the machine learning model is same one used in that paper. And we have the realistic instances, the security control unit complement, 24 hours. So of course we want to use the strong branching to collect the training data, but that's not possible. So here we made some compromise. So at each node we only probe 100 variables, but we keep doing this for like 2 weeks. And then this provided the training example, which are the strong branching scores that we can develop a machine learning model to predict a new branching score in a new instances. Right? Okay. So this is our result. So basically, this is the actual value. This is the predicted value. So if your prediction is good, this will be a perfect straight line. But if not, you spread across the whole area, right? So this is the result from the benchmark algorithm, where you only develop a single machine learning model. And this is the result where you develop one machine learning model for one variable. So this is the most exhaustive way. So you can see that this prediction is much better than that you only have a single model for all your branching decisions. And then we talk about several grouping strategy, right? Grouping by name, grouping by time, grouping by generator, and they are somewhere in between.
So let me see, what is the actual value here?
The actual value are like the strong branching score. Yeah. And this is the predicted strong branching. So basically, we're trying to mimic strong branching with a model, predicted model. So how do we test the effect on the branch and bound process? So what we do is that we put a node limit to 1,000. So basically, you solve using our in-house branch and bound solver for 1,000 nodes. And then at the end of the 1,000 node, you look at the MIP gap. So here is the most infeasible. That's the worst, right? And here is our benchmarking. That's the benchmarking. The average gap after 1,000 node is 0.54. So if you look at this one, this is our per variable one. So this can close more gaps than the benchmark algorithm, and we go down to 0.40. and you can see that the grouping, expected, right, in between. So this is for one solid node. So if we have more nodes here, 10 solid nodes, and we can see that has more effect. And this is the benchmarking, and we can see that with the one solid, we can close even more gap. So from a 0.45 down to 0.229. And of course, this grouping, is somewhere in between. So this is the impact on the result. Okay, so now I'm going to talk about a package we developed based on this idea. So we have seen that, although I just talk about this strategy for security constraint unit commitment, but you have seen that all these strategies are actually quite common. Redundant constraints, feasible solutions, patterns, branching, these are very common for any mixed integer program. So we developed this MIPLearn package. It supports Palermo, jump, and also can take on MPS file. Easy to use, extensible. You can define your own learn feature. You can develop your own machine learning model. So we have the primal solution component, which help you to predict a high quality, good solution. Also predict the redundant constraints, branching priorities. We can also predict the objective value without solving a MIP. And also, we provide a benchmark instance. So this is just some screenshot from the package. So basically, for typical usage, you first solve the training instances. You create a solver, solve all of them, and you fit to the training instance, and then you do test. So this is very simple to use. And you can define your own features. For example, if you don't want to use the whole data as a feature, then you can define your own feature. Yeah, so these are the major components. So let's look at something. Yeah, so we can do customization. You choose we have some default classifier, but also you can develop your own as long as it support, like sklearn, these things. You can adjust the aggressiveness. For example, when you fix in variable, how aggressively you want to fix, so that kind of thing. All right, so this is another package which is very relevant. So this is called unit commitment JL. We have built this package for ease research on the security constraint unit commitment problem. So we implement a major formulation for this, and it's very extensible. Currently, it supports Julia. So we are collaborating with the MISO, which is the power market, and trying to make it more realistic. And also now we are developing market clearing package using this software. So if you're doing a unit commitment problem, you don't want to write everything from scratch, please check this out. This can be very useful. Okay, so benchmark. We have seen this. The whole idea works very well on the power problem. So what about in the other problem? And so this is the traveling salesman problem. Results. So basically, you have this, formulation, and with the subtotal elimination, right? And the subtotal elimination constraints, actually, you can consider that as redundant constraints. You can add them only when you need it, right? So using the same learning idea, we can see that the solution time can be get down to like this part. This is like exact solution. So basically, This is the optimal solution. And when you be more aggressive and fixed in variable, that kind of things, and the solution time can be further reduced. So these are the solution quality, right? So, of course, for the exact approach, you get the same optimality gap. But even for the heuristic, you still get like 1% solution quality. And this is very good if you consider how much time you spend on solve it, right? Okay, so this is the prediction on the upper bound. And this is another problem, maximal weight stable set problem. For this problem, I think the things make the work is a branching priority. So this is also a very challenging problem. And you can see that if we keep the optimality here, we can reduce the time by half. But if we want to be more aggressive, we can get here. Okay. And this is the optimality gap. Not bad, right? So this is but even for the heuristic approach, you can still have a very good optimality gap here. So that's show that it works on general mixed integer program. All right, so for some future work, I think we are pretty much done with the branching things because now the branching is a very heated, space, and more importantly that everything you do on branching, it's hard to put them into a commercial solver that can solve real problem. So now we are focusing on the LP regression, especially for large MIP. The LP solution time is quite significant, so we can reduce the LP size. The other thing we are looking at is the cut generation, trying to find the cuts that are commonly useful for similar instances. So yeah, that's all I want to talk about. So in the end, I want to appreciate our funding support from the Argonne LD-RD program and the Advanced Grid Modeling program under the Department of Energy Office of Electricity. Yeah, so that's it. Thank you.
Okay, so because of the time limit, so we will first take maybe 3 questions from the audience in the room. Then, if the time allows, we will take questions from the Zoom. So please ask your questions.
Please.
Thank you very much for this informative talk. One thing that I would like to check is so when we are solving, like you said, a repeatedly solved optimization problem, there's an option to cold start or do this machine learning based prediction of some of the starting features, something like a pre-solving step, and then start from a warm point, right? Mm-hmm. So from a resource utilization perspective, have you compared these two approaches? Like, is it worth spending so much resources on getting to a warm start for getting a lower solution time?
Yes, in some situation, especially consider like the instances are, solved in the past. You are not investing, because all the information you're getting is from the past, right? So, but even like in the market things, you can predict the load in the next day, and you have a few instances, you solve it. Because for the market things that you have very limited time window to solve it. So you are willing to spend like maybe 100 machines to solve 100 instances and collect and help you to solve when the actual problem comes into your hand, right? So yeah, I think that there's a trade-off on that. Like we spent 2 weeks on collecting the branching, the scores. So that's a huge, yeah. But this is for research, right? But in a real application, you already accumulated enough instances in the past, and in some situation, you are willing to pay, to maybe cloud machines, to get the training instances.
wanted to ask about distributional impact. So when you solve a day-ahead market model, if you have anything other than the completely optimal solution, there will be slightly different prices and slightly different quantities awarded to different generators. So I wonder if there's an effect where by warm starting, you can kind of persistently have biased effects toward particular generators on the system, or if you or if anybody has raised that as an objection for starting.
Yeah, I think that's a good question. I mean, let me see. If you do these heuristic things, you fix the variables, right? That do affect. Yeah, you may prefer, especially when you have like a 0.1 percentage in optimality gap, you may have like a lot of optimal solution, right, within that gap. That could be something, yeah. But if you don't do the heuristic things, for example, you give the feasible solution, but I don't know how the MIP solver, commercial MIP solver, make use of this initial feasible solutions, but I don't think they fixed there. I think maybe that's served as a upper bound kind of things. I don't know. Yeah, but I think that's the question we haven't looked at yet. Yeah, thanks.
Yeah, I was just wondering what your thoughts would be about like the MIPLearn. So like you have all these sort of nested models, and having one that's essentially like a higher order learner as a way to optimize the implementation of these like smaller models. Is that kind of that's what the branching mechanism sort of like doing, right? But wondering what your thoughts on that would be then to have a sort of ML-learner on top of these already established models trained.
Sorry, can you speak up a little bit?
Oh, sorry, yeah. So I was just wondering what your thoughts would be about a ML-learner, because you have these sort of like nested models already trained, and as a way to apply these models that are already in existence and already trained to a new sequence.
I'm not sure I get your question.
But maybe that's what you're kind of already doing with the branching.
So, Jacob, can you help? What is the reference?
Yeah, I'm not sure I understand either.
Since you already have these like models that are trained, and you're already using that as the warm start, so you're taking this model that's been trained, and then you're using that as the basis for a new trained model. That's what you're essentially doing with the warm start.
So the warm start take a potentially feasible solution and give that to the MIP solver. The MIP solver will use it in some way.
Yeah, and then I was just wondering about what your thoughts might be on a higher order learner, since you already have these existing models, as to like how to allocate these or how to apply these models that have already been trained into warm start.
You mean like pick the best approach to apply?
Yes. Yeah.
Yeah, I think that's possible. Yeah, because they work from different approach, like cutting, redundant constraints, feasible solutions, optimal solutions. So I think, yeah, like, yeah, I haven't just thought about that yet. So maybe there is some higher order, learning things that can help you to optimally customize each method. We haven't done that yet. I think that's a good perspective. Yeah. Thank you. Yep.
So okay, so I think this is the end. So if you have more questions, so please just contact Dr. Feng with this email. And if you have some interest in his research work, or if you want to find an internship job in the national lab.
Yeah.
Okay.
Thank you.
Okay, thank you very much.